The last time we started setting up TSS task segment. Task state segment. And we had some trouble with the 286 manual that we use. And you pointed out that perhaps I have an error here in the attributes for TSS. And it took me a while to find out, but there really is another error in documentation. So let's first take a look here. I noticed that this is in fact a task gate, not a TSS descriptor. So I started setting up descriptor according to this text, which should be more accurate. But then I found out that there is another figure which is this time this is a TSS descriptor instead of task gate descriptor. So these two diagrams has been swapped around. And this tells us that there is this B bit, this is a busy bit of task state, and then it should be one above it. But let's take a look at another part of documentation. Here we have various system segment descriptors covered in general. And this type, it should be 1 for available task state and 3 for busy task state. This means that B bit is not the lowest one, it's the second bit. The lowest bit should be set to 1 in either case. 1 and 3 both have the lowest bit set, and 3 has also the second bit set, so B, busy, is the second bit. So there was another error in that diagram. And we should change this accordingly. Since we want to load this into task register, we need one that is not busy. And also we cannot do this here because we use a selector to set up task state, and selectors do not work until we are in protected mode. So let's just move with this to protected mode part. And let's try running it like this. Okay, everything works. Great. Now that we have task state segment, let's take another look at it. Here we have the initial stacks for privilege levels 0, 1 or 2. And these values are used when we call a higher privilege from a lower privilege. So to jump to a lower privilege, we used return instruction, and when we do a call to a higher privilege, the reverse operation happens. So then a new stack is set up, taken from TSS, and the old stack SSSP is stored on the new stack. So for the far return that crosses the privilege levels, stack contains not only CS and IP, but also SS and SP. And this is why we need to have this value for the stack set up in TSS. Now let's try this call in the opposite direction. After we write a message, let's do some call to a higher privilege. So to the original code selector, not this one, which is for ring 3. And for this purpose we need a call gate, because this lower privilege code is not allowed to just call it like this. Let's make some tester routine. It should just return some character so that we know it executed, and return far. This should not work, so let's test it. Oh, perhaps even though it doesn't work, we should have a way to see the result. Oh well, it worked. It displayed the character. Well, I was not expecting this because documentation makes it clear that call to higher privilege level can only be done through a gate. The reason for that is that gate then sets up what offset within segment of higher privilege is called to make it impossible for a lower privilege program to jump to any offset in a higher privilege segment. Because once you are able to jump to any instruction, then you can try to manipulate these instructions to do what you wish. So the fact that this worked is a bit strange. Perhaps it's some emulator fluke. We should not be able to use it to read some code, for example. But it allows that. It allows to do that. Are we really in ring 3 then? Let's try to display CS selector. Nothing happened this time. But perhaps this is our interrupt handler that is not working correctly. No, exception happens correctly. Let's use a different color this time. Okay, this is a plus character. Plus is to be in hexadecimal. So this is in fact ring 3 selector, just as it should be. What about reading an IDT? Oh, this time we have an exception. Yes, I'm trying to find out why this works without the gate. It should have caused an exception, and it did not. Oh wait, this was a bad test. IDT selector. But yeah, exception anyway. So some protections are working. And with code selector, there is no exception, and this is very strange. Let's make code not readable. Exception, okay. Yeah, and this is what is really strange, that it allowed us to call higher privilege without the gate. For now, let's try to set up a gate anyway, just to see how it works. And this time we can use any offset. Oh, we have an exception this time. Oh, I think I know why. This gate should be accessible for ring 3. Yeah, it works now. Through a gate. And we can see that this allows us to put any offset here, and this should not matter. The code that gets executed is always the same, because this is the gate that controls final segment and offset. I'm going to leave it till later to find out why the call without gates worked, because I'm not sure if that is the limitation of emulator or some problem on our side. I may need to test it on actual hardware and not emulator. Please forgive me, I turned off my microphone for a second by mistake. So what was I saying? That call instruction uses this value to set up a new stack, and on this new stack for ring 0 it stores the value of stack pointer for ring 3 and value of CSIP of ring 3. So all these values are stored on the new stack, and then upon return all these values are restored from this new stack, and we are back to using an old ring 3 stack. Now, some of these fields are marked as never altered, and the other ones are changed during task switch. So when we do a task switch, we are not going to do this now, but if we did a task switch, then CPU would store here all the values of the registers before switching to a new task. But some of the fields CPU never touches, so we set up these stack pointers in the TSS, and CPU would never do this for us. We need to have this set up, and similarly we need to have LDT selector set up. Add offset 42. So let's change it to 42 and add LDT. This is also given through a selector, but to be able to do this we need to have an LDT. And what is an LDT? As you can see, LDT is something that gets switched when you switch tasks, and this allows for a so-called process isolation. This allows each program having its own task segment to have its own set of descriptors and selectors that would not be accessible to other programs. Because this first layer of protection is that we have some descriptors that are ring 0, like these ones, and then a program on privilege level 3 is not able to use them. But if this table contained segments for all different programs running in ring 3, then one program could read or write into a segment of another program because they are both on the same privilege level. So LDT is there to isolate these descriptors for different programs in a different local descriptor tables. So in global descriptor table we just leave the descriptors that are on privilege level 0 and important for system and shared by everything, while any segments that are important only to this program, current program, would be in local descriptor table. And as you might recall, these local descriptors selectors for local descriptors need to have additional bit set. So we need to modify this macro that it would set up selectors a bit differently for us. So let's add an argument, and when this argument is 1, then we should define selectors with an additional bit. Now we also need a descriptor for LDT, and this is one of the special descriptors. We have seen them earlier. This descriptor is very similar to task state segment descriptor. It just has value 2. And we need to set up addresses here. And then load the table. Let's see if that still works. Yeah, it works, but now with local descriptors and local selectors. Now if we had another task set up with another local descriptor table, then we could switch to another program, and the segments that this program used would no longer be visible to that other program, because local descriptor table would be a different one. And another thing we could do is we could set up this initial TSS. We could set up the values, initial values for registers, including CS, IP here, and just switch to this task instead of loading it through TR like this. Or perhaps we should make another TSS. I'm going to leave it for another session. Right now, what it is interesting to me is the interrupt handler. What stack does it use? Because when we do a call, then we know that this switches stacks. But does interrupt use the same stack that was used at the point where it occurred, or does it switch to a ring 0 stack? So before we hang, let's display some additional information. Okay, perhaps we can use just a breakpoint. Wait, this is not a breakpoint. Some different exception happened first. Oh, perhaps breakpoint is a privileged instruction. I don't remember. No, it should not be. This one is a 0F. So we were using a ring 3 stack in the interrupt handler. Oh, I see, there is a problem here. This gate is itself is a ring 3 descriptor, so we should be using it this way. Yeah, I have this feeling that emulator is sometimes not as strict as original CPU might be. But maybe I'm wrong. I'm going to test it on a real hardware anyway. But not now. Okay, so I found out what my mistake was. I have left this bit set in code segment, while it was not really needed. This, as you can see, is bit conforming, and this is exactly the bit that allows code segments to be used across privilege levels. And we do not really need that here. So I should clear this bit. And now, in addition to calling through a gate, let's once more try to call directly. And now the first call returned correctly, but the second call caused protection exception. So now we have protection scheme working correctly. And the ring-free program is no longer able to call ring0 code directly. It can only call through a gate, and gate has an entry point set up, so a ring-free program cannot decide what offset to jump to, because gate only allows one entry offset. So this method no longer works, and it should not work, because this is unsafe. We can only call ring0 through a gate. And also another detail, when I tried to invoke interrupt directly through this instruction, but it could be just any, I could try to call like DOS interrupt. Let's try it even before. Then also protection exception happens. And the reason for this is that when a program tries to invoke an interrupt on its own, this so-called software interrupt, this is like calling a procedure, in fact, and program is not allowed to do it unless interrupt vector itself has a privilege level allowed for this program to call. So because in IDT we have all exception handlers that are ring0 handlers, then a program cannot call them directly. So trying to do a software interrupt causes a protection exception. But with our gate to ring0, we could try to let a program set up an interrupt vector, perhaps. So let's change the tester routine to be something like setup interrupt vector. We are in ring 0, so we can access IDT table. This is an offset into IDT. Oh, perhaps we should choose registers in a different way. Oh, that should be better. Now we can write to the X. Selector and attributes. This should be the attributes. And the attributes are going to be no, perhaps this should be just a trap and ring 0. Ring 3. Now let's copy an exception handler but make a ring 3 version of this. And write to a different place on the screen. Perhaps even a different color. Now the function that we are calling in rig 0 is now this one, setup interrupt vector. We set up vector for interrupt 3. And then try to execute that interrupt. And instead of hang, we should do a normal IRET. we have tester somewhere. See what happens. It worked. This is written by our ring 3 interrupt handler. So what we have here is we now use the gate to ring 0 to call a routine that is able to modify interrupt descriptor table, which of course from ring 3 we would not be able to modify it. So we use this routine to set up our own interrupt handler for ring 3. This time it is a descriptor that allows for a ring 3 code to handle an interrupt. Therefore, we set up interrupt 3 with our handler called trap, and then we execute a breakpoint instruction that calls interrupt 3, and this interrupt ends up handled by our trap handler. That's all I had to add today. Thank you.